Bobby Ahalia, and he will actually talk about string M-theory prediction for particle physics and dark matter.
So I'll put this mug here because I co-organized a couple of conferences on G2 manifolds recently with mathematicians, and the opening talk of the last one was by Simon Salomon, who was one of the first people to construct a G2 manifold, and he had a mug. He had this mug to open his open the meeting, and he kindly gave it to me at the meeting. Although I'm not going to talk too much about G2 manifolds here. So I'm sort of going to give a survey sort of overview of some of the sort of way that how sort of mature understanding, let's say, that's developed over the sort of past 5 years in thinking about an approach to string theory phenomenology with Gordy, Piyush, and our other collaborators. So we wrote a review a couple of months ago, if you want to have a more detailed look at that. And then more recently, we had a paper which is talking about this Fermi 130 GeV tentative gamma signal that Ben mentioned. So we think of string theory as a framework for describing different physical systems, just like quantum field theory. And quantum field theory describes infinitely many physical systems, and the standard model of particle physics is just one of these. String theory also describes infinitely many physical systems, and it's sufficient that only one of these describes our universe. So by studying only those solutions of the theory with low energy supersymmetry and ground unification, our aim is to extract generic quote-unquote predictions for particle physics experiments. And this is clearly a complementary approach to the sort of statistical or anthropic approach to the landscape that people like Mike Douglas and others have been working on. So just to emphasize the difference, in the sort of landscape approach, there the idea is to ask how probable is it. I mean, what is low-scale supersymmetry breaking more probable than high-scale supersymmetry breaking? So we don't do that. What we do is simply assume that we have low-scale supersymmetry breaking and possibly ground unification, and then try to extract some predictions. So one aim of the talk is to demonstrate that this is actually a useful approach, and the predictions that come out of it are currently being tested. And the basic predictions are being tested to the level that, within a year or so, they'll be ruled out if they're not true. So here's a summary of the basic predictions before I give some of the details. So the very, very early universe, that means sort of after inflation, or whatever generates the density perturbations and expansion. But before BBN is actually matter dominated, not radiation dominated, as many model builders tend to assume. So this matter here is actually just the moduli field, so it's the low energy remnant of the extra dimensions, and so string theory predicts a non-thermal history to the universe. Dark matter turns out to be predicted to be consistent, to be composed of both axions and WIMPs, and these WIMPs have a characteristic feature that they're sort of like WENOs, so the fermionic superpartners of the W0 boson of the standard model. a monochromatic photon signal should therefore be seen, because these guys do have a cross section which is large enough to be, for the Fermi data, for the Fermi satellite to be sensitive to this, as we'll see later. The squarks and sleptons, so the scalar superpartners, are beyond the reach of the LHC, and that's related to this matter-dominated early universe. And in the consistent models where dark matter and all the other things come out consistently, gauginos, including the gluinos and the WENOs, will eventually be observed at the LHC, and typically their masses are TeV or below. This scale, so in Ben's talk he was talking about squarks and sleptons being TeV-ish or below. We're certainly beyond the TeV scale in that sector, and that pushes up the Higgs boson mass. And if you look at, for example, the simplest case that we understand well, which is the M-theory case, there's a correlation which occurs with Witten's solution of the doublet-triplet splitting problem, which fixes the value of the Higgs Zeno mass and gives you a sort of range of Higgs masses between about 122 GeV and 129 GeV. So more details of some of this phenomenology will be given in Gordy's talk. He will talk about the Higgs. I'm not sure if you can see the rest of this, but Piyush will talk about the Fermi data and our interpretation of it, and Ran Lu, who's also here, will talk about the more detailed LHC phenomenology. So the preliminary ATLAS and CMS data from last year are indicating an excess at around 126 GeV. There have been, so Ben mentioned a couple of analyses of the Fermi data. There were some earlier ones, and all of these are concluding that there is an excess of photons in this energy at around this energy. And both of these are consistent with these generic predictions that come out of this way of thinking about string theory and its interface to low energy particle data. So the key to all of this comes by thinking about extra dimensional physics, namely the moduli fields and the axion fields. And an important role is played by understanding what the moduli potential looks like. So it's really, in that sense, if not stringy, but an extra dimensional input which is leading to all of these predictions. So I'm now going to say a few words about what we mean by a generic prediction. So what sort of quality does a prediction have to have in order for it to qualify as being generic? So generic is certainly not a theorem, so that means that it could be avoided in special cases, but presumably one would have to work relatively hard to make a non-generic example. So here's an example in the context of quantum field theory. So just asking what the generic predictions of string theory or quantum field theory are is not a good question, apart from things like CPT and spin and statistics and so on, because we have an infinite number of quantum field theories and they describe all kinds of stuff. Here's an example of a much better question. So let's consider the class of four-dimensional non-abelian gauge theories with chiral fermions, hierarchical Yukawa couplings, and spontaneous symmetry breaking. Then we can ask, what are the generic predictions of those theories? And the answer is that you'll have charged currents, massive vector bosons, and a rich spectrum of three-body decays of heavy fermions into lighter ones. Then you can view the discovery of the muon, the tau, the W bosons, and other standard model particles and their decay properties as a verification of these very generic properties. So I think this is a very nice example of a generic prediction. So, and the aim is to elicit generic predictions about beyond the standard model physics within the string and M theory framework. I don't need to convince you guys of how one justifies some of our basic assumptions. So how do we, for example, justify our assumption that solutions of string and M theory exist which reduce to the standard model at low energies? Well, we all know that in 1984, Candelas et al. Showed that a generic four-dimensional solution of the heterotic string theory is a non-abelian gauge theory with multiple generations of chiral fermions and hierarchical Yukawa couplings. And with post-string dualities in other limits, type 2a, type 2b, G2, and so on, analogous statements are also true. So the assumption about having, we have to assume that we can get the standard model at low energies in order to say that we want to make predictions about what's beyond it. So that's justified here. And I don't, so the assumptions about low energy supersymmetry and ground unification are well motivated, and I'm not going to, just for lack of time, not go into the reasons for that. So now let's discuss moduli problems and moduli solutions. So moduli are scalar fields with which are very weakly coupled to matter, roughly by the Planck scale, and they are the low energy description of the extra dimensions and are generic in the sense that in the typical way that we think about string compactification, moduli are there. So in the supersymmetric limit, they are massless. And in fact, that's sort of where they get their name from, because they really describe the moduli of the extra dimensional manifold, Calabi-Yau or G2, or depending on which limit you're working in, and they are the moduli of that manifold, but in the supersymmetric limit. So their masses, so once supersymmetry is broken, their masses are expected to be of order the supersymmetry breaking scale, which is characterized by the gravitino mass. In fact, it's quite difficult to arrange the masses of these moduli fields to be much larger than the gravitino mass for all of the moduli fields. So there's been various work on that over the past 5 to 7 years, and this simple statement, which sort of in the effective field theory level is a statement about supergravity, but with a more concrete setup like a compact Calabi-Yau manifold for the extra dimensions, one can make more precise statements, has very far-reaching consequences, and this is a real key to the subsequent things I'm going to say. As far as I'm aware, we don't have any counterexamples to this statement in cases where the moduli potential is fully understood, in the sense that we understand isolated critical points of it that are stable. So we'll henceforth assume that there's at least one modulus whose mass is roughly the gravitino mass.
Sorry? I disagree with that.
Fair enough.
We can select.
Okay, if you want to talk about it later, we can talk about it later. I'm happy to discuss it now as well.
Okay, wait, okay. Now you say. Okay, so.
No, let let him go ahead because otherwise the talk will be over.
Okay.
Well, I've said this to you many times. This is the first time you've disagreed.
I don't disagree, probably you didn't understand.
Well, anyway, that'd be good to have some discussion. We'll learn something from it. So, one of the main problems with having moduli at the supersymmetry breaking scale is the cosmological moduli problem. So what happens is that when the Hubble scale becomes, so you have some Hubble scale in the early universe, it's usually high in most models of inflation, at the end of inflation. And so as the universe expands, the Hubble scale decreases. It at some point becomes of order the modulus mass. At that point, the moduli start oscillating in their minimum, and they quickly dominate the energy density. And that leads to a matter-dominated universe. So that's where this non-thermal history comes from. But a bit later, the moduli will decay when the Hubble scale becomes of order their decay width, which is this smaller scale. And in general, they can decay to any allowed standard model particle, because typically they're heavier than the standard model particles, and they couple sort of universally in some sense to matter. And if you actually put numbers in here, so if you take TeV scale for this mass scale, this actually happens during the nucleosynthesis of light elements. So that's a bad thing because these particles are charged. You have leptons, they're hadrons as well, and the nuclei get disassociated from this process. And this nice model of Big Bang nucleosynthesis, which is very, very successful in predicting the abundance of light elements, gets ruined. So, on the other hand, this is a cubic dependence in the mass of the moduli. So, increasing the moduli masses by a bit, you can easily avoid this problem, and that bit is essentially an order of magnitude. So 30 TeV is a representative number that we use for doing this. So then the moduli will decay quite a bit earlier, and everything is consistent. So this is the simplest solution to this moduli problem, but it leads to a new mass scale. And what we've been doing is taking this mass scale, taking this simple picture very seriously, and just exploring its consequences. So there are some caveats here, and I think in the next talk we'll hear something about this. So if the Hubble scale is at the end of inflation is less than the gravitino mass, or if there's a late period of inflation where this condition is satisfied, then you can inflate away this energy density in the moduli and potentially solve the problem there. So this could be possible in string theory. One question we would like to ask is it generic in the same sense? Because this is adding more ingredients to the picture, so making it more complicated, presumably making it more tuned. So one would ask the question, how generic is it? In gauge-mediated supersymmetry breaking, the gravitino mass is very, very low, so the cosmological moduli problem is much more severe there, and something like this is required in gauge mediation. You have a huge amount of energy density stored in the moduli. So I'll just spend, so having talked about the general picture, I just wanted to spend a couple of minutes talking about a simple example, which is this simple example in M theory on a G2 manifold. And there, the ideas are very, very simple. Very old ideas, very good ideas. But there the idea was to try and here in our context, the idea was to try and push these ideas as far as possible. So the idea is that strong dynamics will generate the hierarchy between the Planck and the weak scale, and at the same time stabilize moduli and break supersymmetry. So people have been looking at this idea over the years in hadronic theory and then in other corners of string theory. It works very well in M theory because, in some sense, all the moduli in M theory on a G2 manifold are on an equal footing. And so if you stabilize one of them, the chances are you're going to stabilize all of them. And in the simplest model, there are just two integers, which are the ranks of two hidden sector gauge groups, which determine all of the relevant scales and couplings self-consistently. So it's a formula for the Planck scale in terms of, so there's a formula for alpha gut in terms of these integers, Planck scale in terms of alpha gut, the gravitino mass in terms of these integers, and so on. And if you put numbers into that, q minus p equals 3 gives you a gravitino mass in the right order of magnitude, and you can't play with this. This is very sensitive to this, exponentially sensitive to these integers. So for example, if q minus p is equal to 4, you really don't get anything consistent. So this, I'll probably skip this slide. This is a slide about why gaugino masses turn out to be suppressed. Essentially, if the moduli potential is just the moduli potential and there are no other fields which play any role, you'll end up typically in an anti-de Sitter vacuum. And what happens in M theory is that the field which dominates SUSY breaking is a matter field in the hidden sector, and that leads to a suppression of the tree level F terms for the gauginos, and typically leads to a Weno-like LSP. And this is not pure anomaly mediation in the gaugino sector, but sort of similar to it. So another interesting point is the axion, the cosmological axion problem, which is a sort of long-standing problem in string theory, that axions tend to have gut scale decay constants. In a thermal history, which is what's usually assumed, that leads to there's an upper limit on the decay constant, which is way smaller, several orders of magnitude below the gut scale, and one has to work hard to solve that problem. If, as we are saying, the early universe is actually matter dominated, when the moduli decay, they release a huge amount of entropy, they dilute the axion relic density, and then the axion decay constant can be much closer to the gut scale. So one solves the axion relic problem in gut axion relic problem. Similarly, when the moduli decay, if you have a stable neutral particle in the spectrum which it can decay to, it will be produced and it will still be here today. And if you do the calculations, the relic density comes out about right, precisely for this Weno-like LSP. It has the right annihilation cross section, which is a couple of orders of magnitude larger than what for example, a Bino-like LSP would have. And this is what's called the non-thermal quote-unquote miracle, non-thermal WIMP quote-unquote miracle. So one really has to live with mixed axion Weno dark matter in this story. So Piyush will talk a bit more about this. So as has already been mentioned, this 130 GeV, there's some evidence for a photon signal at 130 GeV. And if you fit the actual effective cross-section for this, you get a number which is of order 10 to the minus 27 centimeter cubed per second. Thermal WIMP relics have an annihilation cross-section which is about 3 times 10 to the minus 26 centimeter cubed per second. And as Ben mentioned, the annihilation to photons is typically one loop suppressed. So if you suppress this by a loop factor, you're an order of magnitude below this, roughly. So you can't explain this Fermi signal with thermal WIMPs generically. Non-thermal WIMPs have a much larger annihilation cross-section. So the analog of this number is a couple of orders of magnitude above this, and so they have just about the right annihilation cross-section to explain this signal. And if it's a Wino, then the mass has to be 145 GeV because they dominantly annihilate into Z gamma whenever you've got a photon in the final state. And furthermore, when we fit this signal in detail, it actually is consistent with only 50% of the total dark matter being composed of Winos. So it's completely consistent with the rest of dark matter being made of axions. So that was very nice. It didn't have to be that way, but it is. So I've already said that the scalars will not be produced directly. The gauginos in the simplest models are suppressed, and actually if the gaugino masses are not suppressed, it's quite difficult to make everything consistent with the dark matter constraints. So these are some figures on the axion physics in the non-thermal world and in the thermal world. So this is just to show how much more fine-tuned the thermal case is. So you have to tune by 5 orders of magnitude the initial misalignment angle of the axions for gut scale decay constants. And in the non-thermal case, there's much less fine-tuning and some predictions that Planck may see isocurvature perturbations, so we'll be in some region around here, but not tensor modes, because these would already, if Planck saw tensor modes, they'll be already ruled out by existing isocurvature perturbations. The Pamela positron data is consistent with Wino-like dark matter, and lots of further testable predictions. So because you've got this heavy scalar light gluino type spectrum, you expect when the gluinos to decay, Ben actually did draw the diagram for that in his talk. You expect 4 top plus missing energy final state, which is a fairly spectacular thing. More details of the Wino sector that Ran will talk about. Xenon 100 will not see a signal and hasn't seen a signal, but if we push things, a bigger detector may see something. So this plot here was shown by Gordy in the last string pheno meeting last summer, and this is what was already shown by Ben. This is just the gamma-gamma signal from last December, and so as has already been mentioned, we'll have an update on this next week. There's more details on the LHC predictions I'll skip. So that's what a multi-top quark event looks like, because the tops so if you produce 4 tops have 3 body decays, so that's a total final state with 12 fermions at least in the final state. We should eventually see those. So I'll conclude now. So the gravitino and moduli masses are in the tens of TeV region. String axions with gut scale decay constants have a non-fine-tuned cosmology and make up a significant fraction of dark matter. We know light particles are also a significant component of dark matter. In the Higgs sector, one predicts a standard model like Higgs, only one, because all the other 4 MSSM Higgses are too heavy, with a mass in this, sorry, this should be a 9, that's a typo, a mass between 115 and 129 GeV, and in models that have doublet triplet splitting solved in the way envisaged by Witten, 122 to 129 GeV. This I've already said. In particular, gluinos are something that we should look for, and the main discovery channel for gluinos would be final states which are top and bottom quark rich, with large multiplicities, per event in terms of particles in the event. So searches with at least 3 B-tagged jets missing energies and possibly also a single high PT lepton from one of the top quark decays is one way to go with this, and Ran will tell us more about some of this later. So this is a very, very exciting time in particle physics. We're on the verge of possibly 2 incredibly significant discoveries. I hope that I've convinced you that this sort of general approach to string theory phenomenology leads to predictions which are being tested now at the LHC and at dark matter indirect and direct detection experiments. And if these tentative signals from the LHC and the Fermi Large Area Telescope are strengthened or positively concluded, let's say, these could represent the first positive tests of string theory physics. Gluinos, so if the Fermi signal is real, then one should observe gluinos potentially by the end of this year. On the axion side, if Planck detects isocurvature perturbations, that will give us a handle on the axionic component of dark matter. So, thank you very much for your attention.
I would like to come back to this, the comment that Ran said before, which I must say I agree in the sense that, okay, I don't disagree that you can have models of the types that you mentioned, saying the masses of the moduli, but certainly you cannot say that I'm generic. I mean, there are models in which, for instance, all moduli have masses much bigger than the gravitino mass, in which you can stabilize the module in a supersymmetric way, for instance. There exist models.
Can you give me the reference?
Yeah.
What is it?
And the second is the models in which there is moduli in which their mass is much lighter than the gravitino mass. Lighter on the source.
If it's lighter, I have no problem. Yeah, if it's lighter, I have no problem because it doesn't solve the problem.
But you cannot say that it's generic. Then you can say that this is your prediction, some particular class of models. But I don't think that you can characterize generic.
So what's the reference? What's the reference for a supersymmetric vacuum with all moduli?
Just take a Calabi-Yau space with no only one type of moduli that you can stabilize using using the superpotential, only complex structure. That's
Cala-
my case.
Calabi-Yau manifolds always have Kähler moduli, so you can't have such things.
I mean, okay, yeah. It doesn't have the name of Calabi-Yau, but there are models in which there are no Kähler class.
I'd like to see
Or
the
you can
example.
stabilize both using, for instance, magnetic fields and on the one side, and for the Kähler class moduli, and in a way that preserve n equal 1 supersymmetry. I mean, you can also do construction using minimal models as conformal blocks in order to have such model. I mean, I don't think you can say that.
Well, minimal models will not stabilize the dilaton, right? So,
Of course. Using, I mean, the dilaton is a complex structure.
yeah, maybe you could give me some references. That would be useful.
Maybe I could help Ignatius a bit. Could you show us the superpotential or Kähler potential you're using for your generic predictions?
I'm not writing down a superpotential and a Kähler potential for all, classes, but we started thinking about this in a specific context, which was M theory on a G2 manifold, and then we realized that the conclusions were much more general. So you can show, for example, that in any string compactification where the potential depends only on moduli fields, that if you have a supersymmetry breaking minimum with approximately 0 cosmological constant, that the mass of the lightest scalar field of that system is of order the gravitino mass. It's just a theorem that follows from supergravity, that follows from the work of, I listed some references there. So it's much more general than picking a specific class of superpotentials.
But that theorem assumes that the sectional curvature in the S goes in a direction is not enhanced above.
Yeah, but we know.
Scale.
But
So,
we know.
but there are models. I think what Ignatius is talking about is that there are models. I don't know whether they are string compactification, but there are models in which that could be enhanced.
So we know.
So, but
so the
there are
sign,
limits.
the sign of that
geometrically.
sectional curvature term, for example, for compact Calabi-Yau threefolds, is related to the intersection numbers of the triple intersection numbers of the Calabi-Yau, and for half of Calabi-Yaus it will have one sign, and for the other half of Calabi-Yaus it will have the other sign. And so for half of all Calabi-Yau compactifications you can show it's true.
But
Secondly, if you're at a generic point in the moduli space of the case that you can't exclude by that argument, the curvature is of order 1.
I
So,
agree that I don't know of any string theory examples.
so it's not
But
a,
there are bottom-up models like Kitano's model, for example, which are relevant for gauge-mediated supersymmetry breaking, where you can enhance it. But anyway.
yeah, so
Another question.
So you started arguing that the moduli had to be above a certain mass for these cosmological reasons. But then you're putting in an extra assumption about getting a weak scale, right? I mean, you have a pretty serious little hierarchy here.
yeah,
It looks unnatural from bottom-up point of
I'm
view.
not worried about that little hierarchical. I actually think that moduli physics is telling you that there's a new scale there, which is 10 TeV or so, and something is happening at that scale. And
So you do have to put in this hierarchy by hand in a sense. Put in the
I'll
weak
talk
scale.
about that in
or
detail.
press, right?
yeah, so Gordy
I'll
will
talk
tell.
about that in detail.
Okay.
But the thing is that just these simple arguments about moduli and axion physics, they lead to a very, very simple picture, which not only is consistent, but is correlated with a Higgs boson mass of about 125 GeV.
Given that
And-
you fix the weak scale, given that you fix MZ, say. Is that right?
Oh yeah. We're
Yeah.
putting in low energy supersymmetry. We're only looking at string theories that have low energy supersymmetry. And the correct value of MW and MZ.
One last question.
Yeah.
You are still in?
Well,
Yes.
just wait.
So second to last question.
Yeah, so when the moduli decay, the universe is not a zero temperature. There will be some sort of finite temperature.
Yeah, it's a few MeV.
Here maybe. So it's not possible that you get like that zero temperature mass is 1 TeV, then you can get a shift from the finite temperature correction.
What do you mean by the zero temperature mass?
So that's going to be very small. In principle,
It's
there
going to be very small.
because the full temperature is only a few MeV. The finite temperature corrections to the field theory, I mean to the zero temperature mass, will be negligible.
Right.
Yeah.
Just now, many things have been said already, but in your list, the things I disagree, because I wrote a paper in '93 where I was stating more or less what you were saying, and then the last few years, what we have been doing is realizing that some of the things we were assuming were not true. For instance, the couplings of the moduli, they're not Planck effects, but they are string couplings effects. Most of them. One of them, probably the overall, is Planck effects.
Yeah, Planck or string, it doesn't matter
No,
for
because the volume is a big factor. And so you want to get the God scale, the volume has to be 10 to the 6 or so. So in that sense, the difference between string scale and Planck scale is big. And so then the interesting thing about that, I have to tell you, from what we have been doing, is that even though this happened, for instance, the couplings are not so suppressed, many of the moduli can be trapped or something in their potential, and that don't create a problem with the moduli problem. There is always at least one, which is in our case the volume modulus, that is lighter than the gravitational mass. So again, it's against our general belief. But the thing that remains out of that is that the cosmological moduli problem is still a problem. So
Yeah,
that's what at the end, from our conclusion, even though the physics was completely different, at the end the problem remains the same. And then you have to, and in that sense, I agree with you that there is an information.
Yeah, so
But I think that makes the problem probably more interesting, because even though all these things are not satisfied, you always get.
having moduli which are less than the whose masses are less than the gravitational mass, of course, then you still have a problem. If for most of the things I've been saying, having a string scale decay constant for the moduli, it doesn't change too much. Actually, for the case of the Fermi signal, it makes it slightly better if you think about it carefully. So if you look at the numbers which fit the data well best in our paper on for the Fermi signal, it's around string scale.
Okay, I guess that concludes the discussion. Thank you very much again.